I try to imagine a fellow smarter than myself, and then I try to think, what would he do?
Charge up your axons, ready your receptors, and shift your lobes into upper beta phase. You are listening to Smart Drug Smarts, the podcast dedicated to helping you optimize your brain with the latest breakthroughs in neuroscience, nootropics, and psychopharmacology.
Hello and welcome to Smart Drug Smarts. I am your host, Jesse Lawler, here with the 70th episode of this podcast dedicated to the aggressive betterment of your own brain by any and all means at your disposal. We're going to do something a little special for this 70th episode, which is kick off an episode series. And the series isn't necessarily going to be contiguous. In fact, it almost certainly won't. But this is something we've kind of been thinking about for a while, and we're doing a series called Know Your Neurotransmitters. Yeah, neurotransmitters, they're these chemicals that get kicked around between our neurons in the brain, helping and hindering the signals from one neuron to the next, as the case may be. Chemical messengers that make the electrical activity within your brain that makes thinking happen get biochemically pushed in one direction or another. So as we're thinking about things like nootropics and other chemicals that affect the brain, neurotransmitters are really kind of where the rubber hits the road. So in honor of that, we're doing the first of these about the neurotransmitter GABA. That's GABA, all capital letters. The neurotransmitter that kind of reminds you of a DNA strand crossbred with a band from the 1970s. And we're going to be speaking with Dr. Matthew Broome from the Department of Psychiatry at the University of Oxford. He's a senior clinical research fellow. We're going to be talking a lot about GABA and a little about his research into schizophrenia, which he is very interested in trying to delve into what the underlying mechanisms going on within the brain that cause this condition are. If you hang around until the end of the episode, I'm going to tell you about a really, really interesting neurological disorder called Alice in Wonderland syndrome, which is every bit as weird and druggy as you might imagine. But before we get into any of that, let's do This Week in Neuroscience.
Smart Drug Smarts. This Week in Neuroscience.
Okay, so there's a new study from the University of Birmingham and the MRC Cognition and Brain Sciences Unit at Cambridge that is showing how intentional recall of memories is actually something that dampens the ability to recall other related memories. So you try to remember one thing, you're actively remembering it, and in doing so, you're hindering yourself from the future recall of related memories. So remembering one thing makes you forget something else, basically. It's not a doomsday scenario where recalling one memory once is going to completely wipe out something else, but it does apparently inhibit the ability to remember those other things in the future, said Dr. Maria Wimber from the University of Birmingham. There's been an emerging belief within the academic field that the brain has this inhibitory mechanism, but I think a lot of people are surprised to hear that recalling memories has this dark side of making us forget other memories by actually suppressing them. The team of neuroscientists, which was co-led by Dr. Michael Anderson, was able to track the brain activity induced by individual memories and show how this suppressed other memories by dividing the brain into tiny three-dimensional voxels. A voxel is like what a pixel is on a 2D screen, except it's 3D. So you think of little Lego-like blocks divvying up something, and that's what a voxel is. So participants in this study, over the course of 4 selective retrievals, were cued to retrieve a target memory, which became more and more vivid with each trial. But the competing memories were less well reactivated as each trial was carried out. And in fact, they were actually pushed below the baseline expectations for memory, supporting the idea that an active suppression of other memories was taking place. I find this kind of disturbing and weird. It's kind of like if you think about your place in the universe, that we're all just stardust, and what does it all mean? And that can be kind of a scary existential terror sort of feeling if you look at it the wrong way. I kind of have a similar heebie-jeebiness when I think about the fact that our memories, rather than being an accurate representation of where we come from, what we've done, who we are, and kind of being the core of our identity, that memory is like this mushy, inexact, shifting sand kind of thing that every time you pull up a memory, it's changing a little and it's inhibiting your other related memories. Like, wow, that is not the way that I wish the brain worked. But of course, my not wanting it to work that way doesn't change anything. But that's what this study says. Pretty interesting. And we'll put the link up on the website. And one thing that I will not be forgetting is to throw out a thank you to Vince Master, who is the latest person to leave a 5-star review for this podcast on iTunes. He said, I listen to a lot of podcasts, over 20, and Smart Drug Smarts is absolutely one of my top 5 favorite. The wait is well worth it as Smart Drug Smarts edits each episode very well. Truly a quality over quantity project. And hey, here we are we're hitting an episode a week now. I hear you, Vince. We've been a little late from time to time, but those days are behind us now. We're turning over new leaves in 2015. And per the dictatorial mandates of Rhiannon at smartdrugsmarts.com, we are going to be publishing every Friday, including this Friday. It is Thursday as I record this. And hat tip in advance to Anush Tup, our editor, for making this breakneck production schedule actually a reality.
Smart Drug Smarts.
By the way, it's been another good week as far as audience feedback. Got some email introductions from listeners on potential future interview guests, and I've gotten several emails from people who are commiserating with me on some of the difficulties in pulling off a ketogenic diet, but also some great advice on how to make my next foray into that. So do not despair. I'm not despairing. I have been eating a lot of fruit. I have been regaining the weight that I lost during the water fast as my body refills its glycogen stores. I'm almost back to what I was weighing prior to the water fast, but I do have ketosis in my future, so fear not. So now, as mentioned, our inaugural edition of the Know Your Neurotransmitters series, we're going to be talking about GABA. That's gamma-Aminobutyric acid, but everybody calls it GABA. You'll see it written GABA with all big letters. GABA is kind of thought of as the chill-out neurotransmitter, the one that calms you down rather than revs you up. And we've heard a little about it previously when we've been talking about L-theanine, which is one of the compounds in green tea and some cognitive enhancer supplements like smart caffeine. And L-theanine tends to promote GABA within the brain and thus have a calming effect which counteracts some of the nervous stimulation that can come along with caffeine. So the perkiness of caffeine and the calming effect of GABA is thought to be a nice 1-2 punch. But let's dig into the biochemistry with Dr. Matthew Broome. Dr. Broome is a senior clinical research fellow at the Department of Psychiatry at the University of Oxford. He's a consultant psychiatrist at the Oxford Health NHS Foundation Trust and an honorary associate clinical professor of psychiatry at the University of Warwick. Most of his research has been into psychotic illness, particularly in the early stages of illness, and he's used fMRI and cognitive neuropsychology to look at the onset of disorder and symptom formation. We'll get a little into his research later in the interview, but we'll kick things off with the neurotransmitter GABA.
So I guess to start off with, GABA's main role is as the major inhibitory neurotransmitter in the mammalian nervous system. And that implies that its function is predominantly one of inhibiting nerve cell depolarization. So all things being equal, GABA will tend to act such that the nerve cell in which it binds to is likely to have a lower likelihood of firing. So it tends to make the nerve cell more likely to not fire. And I guess it's very important clinically in several different disorders and in treatments we use in medicine, and functionally has important roles in things like regulating sleep, plasticity and learning, as well as coordination of the nervous system.
What would some sort of garden variety examples of proper use of GABA, when one's body would be usefully inhibiting a neuron from being likely to fire?
Okay, so one of the reasons I've got into it is through its role in synaptic plasticity. So I guess as a key part of learning and memory. So we tend to think about memory as being dependent upon synaptic strengthening, and that thought tends to lead you to thinking about sort of excitatory amino acid neurotransmitters such as glutamate. But I think the importance is that GABA has a key role in how memory is maintained and structured in the nervous system. So one of the things I'm interested in with colleagues in Oxford is how those mechanisms work in vivo, and also how those mechanisms may go awry in disease states. But it's important to recognise that there's a role for GABA and inhibitory neurotransmission in this process also. And one of the ways we think this may be the case is in how strengthening between neural networks is managed and balanced homeostatically.
So what would an example of that be in the case of memory formation?
It's more how the memory is accessed and the effect it has once it's been formed, I guess, where GABA comes into play. So I'm sort of referring to work of my colleagues, Tim Vogels and Tim Behrens here. So the idea is that a sort of network of neurons has excitatory neurons inputting onto it. And a memory is formed by how that one layer of neurons then transmits onto the other layer of neurons, with the strengthening of connection being the sort of neural correlate of the memory, as it were. Where GABA comes in is at that second stage, so when the one level of neurons moves on to the second level. They also transmit by side routes, as it were, onto GABAergic interneurons, and those then in turn synapse on the second level. And that's so you get a triggering in layer 2, as it were, of both glutamatergic and GABAergic neurons. So the net effect is one of balance, but of a strengthening between the connections between level 1 and level 2. And the reason that's important is you get a memory that's then formed, so the strengthened connection between level 1 and level 2. That memory is itself in some ways homeostatically balanced out by the inhibitory interneurons at the next level, which means that the memory is as it were, encapsulated neurally, and that's important. We might argue both phenomenologically, so it might mean that you don't get random thoughts flashing into your head in appropriate times, but also is important neurally in the sense that you don't want random propagation of excitatory signals throughout the brain, which could lead to seizures and epileptic phenomena. So I guess GABA is very important in terms of balancing out memory formation. And we think that might be important both in terms of your own mental state, but also important in terms of the wider risk of cell death and damage through uncontrolled firing in the brain.
If somebody had an excess of GABA or, on the other hand, too little, what might some of the effects be subjectively?
So I guess there's a few things you can think about. I mean, I think we can talk about sort of intoxication stage as an analog. So substances we might come across in our lives that tend to work through the GABA system are things like alcohol, benzodiazepines, and barbiturates are the sort of classic example. So these are all ligands at the GABA-A receptor. And the phenomenon of that is one I guess some of us may have experienced. So you might feel sedated, confused, tired, have motor impairment, etc. More subtle things that it might be important in doing and are having a role in coordinating how the brain's dynamics function. So again, one of the things we're interested in Oxford is the role GABA plays in coordinating resting state networks, for example. So how GABA has a function in determining which default states the brain enters into. So kind of pacing of neural activity.
Would that be like circadian rhythms and things like that?
These are very brief sort of millisecond type organizations of connectivity in the brain. And GABA may have a role in pacing those or switching those. What we don't quite know is I guess, how that maps onto phenomenology and cognition. So the thought would be is that if you had a different pattern of different resting states or different pattern of default states, each one would have a slightly subtle analog cognitively and phenomenologically. So I think GABA could be quite crucial in terms of how you experience the world and yourself and reality. There's some data from colleagues that certainly GABA is very important in time perception, and also in sort of motor organization and coordination.
Let's think about where GABA is coming from. Is this something that we're mainly getting precursors of in our diet? Is it something that's secreted within the brain or elsewhere in the body?
Okay, that's a good question. So GABA doesn't cross the blood-brain barrier, so you can't take it externally, as it were. It is effectively a metabolite of glutamate, its main, I guess, competitor. So glutamate's the main excitatory amino acid neurotransmitter, and GABA is the main inhibitory amino acid neurotransmitter. And GABA is a metabolite of glutamate. So it's manufactured by an enzyme called glutamic acid decarboxylase, which is in the brain, and that produces GABA from glutamate. And then, in turn, GABA is metabolized by other neurotransmitters and reuptake mechanisms in the brain.
Dietarily, I mean, you mentioned, for example, alcohol as something that might lead to the upswell of the amount of GABA that's active in the brain. Are there other foods that might have effects there?
I mean, I guess the importance for alcohol is more its long-term effect on this homeostatic mechanism I've mentioned, and I guess that's why it's important clinically. So if you have a constant increased inhibitory tone, as it were, which is what you would have, say, in alcohol dependence, the danger is when that inhibitory tone is removed suddenly. Because what would happen, obviously, in the human brain is that the excitatory mechanisms would try and counterbalance it. So those who are alcohol dependent become what we call, tolerant to alcohol intoxication. They don't appear drunk despite having taken a lot of alcohol, because the excitatory mechanisms within time counterbalance it. And the danger is if you do have something in your diet where you have a predominantly GABAergic tone, and then that's removed suddenly, the excitatory counterbalancing will still be present in the absence of the inhibitory tone. So what tends to happen is you'll get seizures shortly after that change. That's one of the reasons people with alcohol detoxification, can be admitted to hospital, and it's a sort of medical emergency potentially. Yeah. So anything in your diet which does have things like benzodiazepines, barbiturates, those things, even though if you can manage, you could perhaps cope with the consequences after a while. If they were removed, they could be very difficult, and as I say, potentially medically dangerous. It tends to occur classically 72 hours after cessation of alcohol, the kind of seizures.
Interesting. Wow, I didn't even know about that. I kind of always assumed that stopping drinking, if one was a problem drinker, was a good thing. I didn't know that seizures were a potential outcome of that.
I mean, stopping drinking is a good thing, but you have to do it in a managed way. And clinically, one would essentially replace the alcohol with another GABAergic medicine. So what we tend to do in practice is give somebody a benzodiazepine and gradually titrate that and withdraw that slowly, such that you do it safely over several days.
So we've been talking about GABA as a neurotransmitter, but it also has roles elsewhere in the body. Could you talk about that a little?
So it has a role in pain and in the spinal neurons. So I guess another medical intervention is sleep and paralysis, is in managing muscle tone. So GABA is very important in controlling the tension of your skeletal muscles via its effects on the spinal neurons. So another intervention is in people who have impairments of motor function, such as in multiple sclerosis. They may have overactive tone in their muscles, such that they may have spasticity, flexion deformities, and pains in their limb. And a GABA-B agonist, baclofen, can help to counteract that and reduce the tension and the pain in those with neurological illnesses. So yes, peripherally, those kind of functions are important.
You mentioned GABA-B there, and I know that GABA-A and B are the two primary subclasses. Can you tell us what the difference is?
Okay, so both are receptors for GABA. GABA-A is an ion-linked receptor. So when GABA binds to that receptor, it tends to lead to chloride ion influx, again, resulting in the neuron being less likely to fire. The GABA-A receptor also has the sites for benzodiazepines, barbiturates, and alcohol we've talked about, as well as other ligands. GABA-B is a G protein linked receptor, so slightly slower effect of action. And the second messenger signaling is linked to both potassium channels and calcium channels in GABA-B neurons. And those tend again to result in inhibitory actions, either via pushing out potassium, which are positive ions, or by impairing calcium ion flow and preventing neurotransmitter release.
Now, I did a little bit of reading that suggested that the way that GABA is used in the brain is really different between children and adults, and that it can be generally excitatory in our younger years and then changes to inhibitory primarily during adulthood.
Yes, I mean, that's something that I began to read a bit about myself lately, because obviously my interests relate to psychiatric illness. So one of the key questions for us as researchers is why does schizophrenia develop in teenage years and adulthood? And this might be one of the parts of the answers, really, in the sense that GABA does have changes throughout development. And also GABA's function is really very important in how the brain develops itself, in terms of how nerve cells set up sort of connective pathways and grow, and how these functional dynamics of the brain develop. So there's certainly a developmental component to GABA in the nervous system, and that might be of relevance both to schizophrenia and autism.
Can you tell us a little bit about the studies that you've been involved with, what you're working on now, and where the rubber meets the road with your research?
So at the moment, I'm at the stage of planning some research looking into GABA in schizophrenia. So I'm working with colleagues in Oxford I've mentioned, so Tim Behrens, Tim Vogels, Mark Woolrich and Paul Harrison, to try and translate some of these tasks and models we've discussed into a clinical population. So our interest is really to begin examining it in vivo, whether some of these mechanisms that GABA has a role to play in may be impaired in those with schizophrenia and psychotic illness. So the thought would be is that if the plasticity mechanisms are awry, so the interneurons we've mentioned don't adequately counterbalance the excitatory strengthening, then perhaps you have a memory floating around in your brain that you access inappropriately, that becomes more salient, pops into your consciousness too often. And the thought would be, is that a very early stage of some of the unusual experiences that might begin in schizophrenia?
That's fascinating. It also makes me think of obsessive compulsive disorder and some of these other things where people feel like thought loops and ideas that they can't shake out of their head.
Exactly. So that's where our kind of thinking is going. So is this GABA counterbalancing, or as we call it sometimes anti-memory, is that kind of quite key in allowing the memories to become cognitively encapsulated, to be accessed at appropriate times? And without it, do they subjectively run a bit awry and become uncontrolled and perhaps a source of anxiety and concern, and potentially with other mechanisms could lead into the symptoms we know of schizophrenia, such as delusion and hallucination? The more general element is also GABA's role in coordinating functional activity. So in addition to looking at the role on plasticity, we're also going to examine the nervous system of those with schizophrenia using MEG to look at how they enter into resting states, the general synchronization of the brain. So the thought would be is that perhaps these people are struggling to coordinate parts of their brain together, and that may also have a phenomenological correlate, perhaps in terms of time processing, of perceptual coherence, and also just different cognitive states they can enter into. So yeah, the proposal at the moment is to try and translate some methodologies developed in the non-clinical population into a clinical population using MEG, high-field MRS and fMRI.
Where do you think this line of research will be like in a year or 2 years from now? What are you hoping to accomplish?
My goal would be to hope that the research would allow us a way of conceiving of psychopathology differently. So rather than seeing it as a disorder of brain function not working correctly, more to reconceptualize it as a problem due to dynamic integration and problems in plasticity. So I guess that's where I see the GABA approach being quite interesting, allowing us to think of a more dynamic conceptualization of symptoms in schizophrenia. And I guess a long-term goal is then once we chart out how these mechanisms might be impacting on the disorder, we can then perhaps think precisely of having a experimental medicine model, really, of describing a problem which then we could perhaps intervene on with various medications. So if, for example, we did demonstrate there was this problem in synaptic plasticity, we could try and perhaps, in the second phase, ameliorate that with one of the GABA-A ligands we've discussed.
Smart Drug Smarts.
So thank you very, very much to Dr. Broome for spending the time with us to kick off the Know Your Neurotransmitter series. We'll be hitting all the major neurotransmitters in this series, and I think there's still some like fuzzy gray area as to what exactly is considered a neurotransmitter and what aren't. There are some things that are definitely considered neurotransmitters and others that are like hormones that are neurotransmitter-like in their behaviors but are not. Anyway, at this point, I haven't even done the research to know where the fine dividing line is, but among the big heavyweights that nobody contests are GABA, acetylcholine, serotonin, dopamine, and glutamate. We'll probably be hitting those big ones first, but also some of their lesser-known cousins, the oxytocins and things like that. But that is all to come in this series. But for right now, let's do the always worth waiting for ruthless listener retention gimmick.
Smart Drug Smarts. Ruthless listener retention gimmick.
So I didn't know this, but there is a neurological disorder called Alice in Wonderland syndrome, and it has a sibling disorder called, of course, Alice in Wonderland-like syndrome. And what Alice in Wonderland syndrome is it's the inaccurate, obviously, perception that parts of your body are quickly changing size, like your hands are rapidly expanding or something like that. And then Alice in Wonderland-like syndrome is basically the same thing, except it just doesn't apply to parts of your body. Like you might feel like the room around you is receding really fast. So both of these are mistaken perceptual feelings about spatial relationships, and this tends to occur in children. Typical age of onset would be around 8 years of age, and this has been a phenomenon that's been known about for a long time. It's not terribly common, but it's not terribly rare either. It's something that science doesn't have a way of scanning for morphologically right now. They're doing some studies to try to find out if there's an identifiable genetic signature for this, but maybe one reason that we haven't really heard about it is people that have this tend to know that it's not real. It's just a very, very strong and compelling misperception, but they kind of know that it's not really happening even when it seems to be visually what they're seeing. These disorders tend to be somewhat correlated with migraine headaches and epilepsy, and people tend to grow out of them. Not many of these people that experience these effects have the syndrome stick around into adulthood. And interestingly, oftentimes sort of doing a perceptual reboot, like closing your eyes and reopening them, can make the symptoms go away. This kind of reminds me of something that I've experienced when I've been lying still for a long time with my eyes closed, like if I'm going to sleep or something, that if you haven't moved for a long time, you kind of lose a kinesthetic sense of where different parts of your body are. And then if your eyes are closed, you could kind of think, gosh, like where's my hand right now? And you don't really know. And then the moment that you give the slightest twitch of your finger, all of a sudden your kinesthetics all come back to you. And you're like, oh yeah, that's where everything is. And apparently there's a similar sort of mechanism at play with Alice in Wonderland syndrome, but kind of cool. People that have Alice in Wonderland syndrome don't seem to mind it by and large. It's just kind of an interesting oddity. I would sort of classify this like synesthesia, the syndrome where people tend to get various perceptual inputs crossbred, like hearing colors and seeing sounds. I'd put this in a basket of neurological disorders that I'm a little bit jealous of people that have them because it sounds kind of fun.
Smart Drug Smarts, the podcast so smart, we have smart in our title twice.
Okay, you heard it. That is the entire episode number 70 for this podcast. Throw a quick little shout out to my dad, who's probably not listening, but he just turned 70 years old earlier this month, so happy birthday to him. The show notes for this episode, as with all episodes, will be online at smartdrugsmarts.com. You can check out everything we talked about here. I'll be back at you next Friday, same time, same podcast, and with the same unflagging commitment helping you fine-tune the performance of your very own brain. Since I haven't harped on it too much recently, I will take this opportunity to mention, if you haven't signed up for our email list, you should do that. Among other things, you will receive very non-obnoxious emails from Rhiannon, who always kind of finds interesting ways to dovetail into the things that we're talking about. And every now and then we'll drop some neuroscience wisdom that completely eludes mention here on the show. So definitely sign up if you're the type who likes to read. But even if you are completely illiterate, have a great week and stay smart.
You've been listening to the Smart Drug Smarts podcast. Visit us online at www.smartdrugsmarts.com and subscribe to our mailing list to keep your neurons buzzing with the latest in brain optimization. Smart Drug Smarts should be listened to for entertainment purposes only. Although some guests on the show are medical doctors, most are not, and the host is just some random guy. Nothing you hear on this podcast or read at smartdrugsmarts.com should be considered medical advice. Consult your doctor and use some damn common sense before doing anything you think might have a lasting impact on your brain.